You see a table in front of you. Wooden, heavy, sturdy. You place your hand on it, shoe 2013, hard, solid, completely solid. No question about it. But if I told you that this table is 99.99% empty space, what would you say? You'd probably think I'm crazy. Yet that is the truth that your eyes were not built to see. This video starts with a question. You 2013, is a solid thing actually solid? And the answer to this question will take you to depths as deep as science has ever reached. Inside the atom, inside the nucleus, beyond the quark, and all the way to that energy where matter and force become one. First stop, the atom. Let's zoom in. Take a small piece of the table. It contains billions and trillions of molecules. Every molecule is a group of atoms. And every atom, U-2013, whether it's carbon, oxygen, or iron, U-2013, has roughly the same structure, a nucleus in the middle, surrounded by clouds of electrons. But here comes the first shock. The diameter of the nucleus is about 100,000th the diameter of the atom, 100,000 times smaller. Understand it like this. If you enlarged an atom's nucleus to the size of a pea, the entire atom would be the size of a cricket stadium. The nucleus is the size of a pea, U-2013, and the rest of the entire stadium is empty, just a few specks of electrons, smaller than dust particles, floating near the stadium's ceiling. So the table you thought was solid is actually a huge pile of such empty stadiums, billions and trillions of stadiums stacked against each other, but each one almost completely empty inside. Now logic says that if something is 99.999999% empty, your hand should pass right through it without any resistance, like you walk through fog, but that doesn't happen. And this is where real physics begins, U-2013, the physics that tells you that the thing called touch doesn't even exist. You never directly touch anything. When you say, I touch the table, what's actually happening is that the outer electrons are pushing against each other. This push is so strong that the atoms of your hand cannot move forward. The hardness you feel is the electromagnetic repulsion between two negative charges. Exactly like when you bring the same poles of two magnets close together at U-2013, they repel each other without ever touching. To understand the strength of this repulsion, one example is enough. The repulsive force between a single electron in your hand and the table is roughly 1 billion times greater than the weight you can lift. That means, no matter how hard you try, your hand cannot break through that electronic wall. And the funniest part is that this wall isn't a solid thing, U-2013, it's just a force. But if only electromagnetic repulsion were at play, what would happen? According to theory, you could overcome that repulsion and force the electrons to overlap. But that doesn't happen, because there's another rule. The foundation of quantum mechanics, 8U-2013, the Pauli Exclusion Principle. Two electrons can never exist in exactly the same quantum state. In the same orbit, with the same spin, at the same energy level, 9U-2013, two electrons cannot occupy that state. It's as impossible as two people sitting on the exact same chair in the same room. Pauli's principle creates a degeneracy pressure. This pressure does not yield to any external force. When you press hard, the Pauli principle says, U-2013, no, you cannot come here. This is the second wall that stops you, and this same wall prevents white dwarf stars from collapsing, prevents your bones from passing through each other, and keeps this entire universe stable. So the solidness of a solid thing is the result of two things: the mutual repulsion of electrons and the Pauli Exclusion Principle. Together, they create an invisible surface called solidity. Solidity is not a property in a single atom. Solidity emerges when billions and trillions of atoms come together to form a crystal lattice, producing a collective behavior. In physics, this is called an emergent property, SHU 2013, a property that doesn't exist in individual components, but arises from their group. Now the question arises, does solid always remain solid? When you take helium-4 down to near absolute zero, it becomes a superfluid. It flows without resistance, climbs walls, and escapes. In that state, it is neither solid nor liquid. U-2013, it's something else. The bonds between atoms change so much that our definition of solid becomes meaningless. Even more extreme is the neutron star. When the core of a massive star collapses, the pressure becomes so immense that electrons combine with protons to form neutrons. The entire matter becomes a dense sphere. Its density is about 10 to the 17th kilograms per cubic meter. A teaspoon of neutron star material weighs about 1 billion tons. Is that solid? It's something far more strange. Its surface crust is extremely hard, but inside, the neutrons behave like a superfluid. So the line between solid and not solid becomes blurry. Now the second question, if atoms are 99.99999% empty, where does weight come from? A proton is made of 3 quarks. Add their masses and you get about 9.4 MeV squared. But the total mass of a proton is 938 MeV squared. That means the quarks contribute only 1% of the mass. Where does the remaining 99% come from? The answer is binding energy. Quarks are held together by gluons, and that binding energy is so strong that it converts into mass, according to Einstein's equation E sub mc squared. 99% of your weight is actually binding energy. You are made of energy simply because quarks stick to each other so strongly. And what about the remaining 1%? Here enters the Higgs field. An invisible field pervades the entire universe. 2013, the Higgs field. When fundamental particles move through this field, they experience a kind of resistance. That resistance manifests as mass. So your weight is the result of 3 layers. Quarks from the Higgs field, binding energy from gluons, and then these form nuclei and atoms. 2013, and that's how your body is formed. And all of this rests on top of empty space. Now come back to that table once more. You touch it, and it feels solid. You know it is 99.99999% empty. And here is the deepest point. Your brain is a remarkable machine that converts a huge amount of complex information into a simple experience. It doesn't show you how electrons are pushing or how quarks are bound by energy. It simply slaps on a label U2013, solid. This label is what keeps us alive. If every time we touch something we were reminded of the complex equations of electromagnetic force, we wouldn't be able to take a single step, so solid is a useful approximation. But at the scale of atoms, that approximation breaks down, and that is the most beautiful feature of sciencevideo 2013. It teaches us to see the same thing in 2 different ways at 2 different scales. So the answer to is a solid thing actually solid depends on the scale. At our everyday scale, yes. At the atomic scale, no. It is empty and just a play of forces. And at the quark scale, it is a bundle of energy. All 3 answers are true. Physics tells us that reality is divided into many layers, each with its own laws. So next time you push a wall or pick up your phone, pause and think, U2013, you are touching a pile of emptiness, held together by invisible electromagnetic forces and quantum rules. And you yourself are made the same way. So all of this is a vast, beautiful, and utterly strange interplay U2013, which we call matter, even though it is mostly nothing at all. If you leave here with this thought, then this video has succeeded in its purpose. Thank you.